Hi guys, this is me usually Bhai, and today I'm gonna cover about the time series data. Not actually time series data, it's time series. And time series is actually the collections of data over the equal space time systems, like observations of data. In discrete data we generally do not consider about the time frames, but time series is actually all about times and collection of data over the times. Like here you can see the charts. Here at a particular time t naught we have the data points here. Let's say it's 1, and at time t1 the data point lies here, and all the collected data shows like these patterns, and this is what actually called as a time series. Time series is like here it is non-linear, it is curved curved shape, and which is observed data as you can see here. And today especially I'm gonna cover the time series decompositions. What actually is time series decompositions is decompositions of the all components of time series. Time series components means there are three time series components that are they are trends, seasonality, and residuals. Residuals is an error, noise in the time series. And before diving into the time series decomposition, let's get know let let's know about the components. What actually is trends in the time series is the long-term movements or directions of the data of time series in of data in the time series. Like yeah, I can show you the graph here. Long-term movements means you can see here at time t0 it have gone certain up and afterwards down and up and down and up, and it is quite increasing, like, and reached 8 time t100. Let's say it have reached that data has reached up to the 62. Yeah, it's up to 62 units. Let's say value here we have labeled it. And the how it gonna how the trends is actually shows by these blue lines, and like the graph. Let's say the graph is increasing over the time, and we're gonna trace like linearly. Here we have traced linearly, but trends have no boundary about it should be linear. It also can be non-linear. We'll see it afterwards. And here we have the example of upward trends. Like trends can be different. Like here we have whether the data is increasing, decreasing, or stable over time. Like it can also be like stable over period of time, like at time t0 the data points actually the crest, actually the amplitude here is actually 15, and after a certain time, let's say at t100, again the data can be and the amplitude of the crest, or say let's say the graph can be 15s, which we consider as an stables, and decreasing increasing as we see here, this is increasing trends, and decreasing likewise. If data starts with 50 or 60 value, then over the period of time it gradually decreased at while reaching t hundreds and so on. That are the increasing, decreasing, and stable trends. This generally we can see as an example in the stock markets candlestick charts. We see how the market is going. It's going uptrends or downtrends, or it is stable over the time. That's the trends we can plot, we can trace in the stock market, which is an example of time series. And yeah, time transfer here non-linear and is affected by smoothing techniques like moving average. We're gonna cover the moving average also after these sessions, in next sessions I think. Now another component we have is seasonality. Seasonality refer to the regular and predictable patterns. Here you can see like why this green line is so seasonality means you can see how the data points actually showing the patterns means go up and down and up and down, and it's like crest and drop in the uh, charts here. In something like that we can see here seasonality means fixed time interval, the repetitions of something data at fixed time over fixed time interval, like the sales of Santa Claus dress in December, in Christmas. uh, so and like yearly, like Christmas comes yearly, and the tracing the sales and tracing the seasonality can clearly be seen there, like and how the data is showing its behaviors, how this data series this time series are showing its behavior. That it can be that as such in week, month and quarters, like it comes to seasonality comes seasonality itself says, and seasonals, that is comes in once or twice or thrice. Let's say how the seasons comes and how its natures according considering that the seasonality comes in the time series. And we have an cyclic fluctuations. Cyclic fluctuations, and it seems cyclic fluctuations and seasonality seems similar, but they are actually not similar terms. Cyclic fluctuations is an irregular oscillation in time series that occur over long variable period, which have like in seasonality there we have the fixed time interval, like it can occurs weekly or monthly or yearly or quarterly, but in cyclic fluctuation there is no certain boundary, like it can come if the fluctuations comes today, and it can occur next day, or occurring next day, then after 2 days it may occurs like that. In that sense the cyclic fluctuations show its behavior, and which is not with a fixed interval, it doesn't occurs in the fixed interval. And that's the major difference between cyclic fluctuations and the seasonality. Here you can see the graph. The data is going upward, and how it is showing how the cyclic fluctuation you can trace it. Actually I haven't also understood that how this trace is showing, this graph is showing this cyclic fluctuation. I mean, there is an equal interval, I mean wavelength are equals, and how it is. Yeah, theoretically we have proved that it doesn't occur at a equal interval, but okay, like you can see two stable uh, graph here, and after that we have one fluctuation, let's know one gradual of fluctuations, and then again stables, and not so high, but Okay, let's say it's a high, and again the same labels, and this all are equal. Like I think these two, let's say, let's count as in pair. But yeah, quite confusing here. And let's get into the noise or error. What actually is noise? Noise, previously what we used to know about noises, it is an random data like outliers, yeah. mm, which is with with cause and model performance, we used to say. And same here, as same and as there, that's same in here also. The error noise component captures the random unpredictable variation in time series data that can't be explained by trend, seasonality, or cycles. Yeah. Let's go directly into the charts, and here you can see, like here we have the time series data plots, and how we can trace the noise is like you can see here the peak, high peak here, and again down towards here, and repeatedly occurred here and here and here. Like they actually noise residuals after removing trends and seasonality, removing trends and seasonality residuals. Oh, look at this is no abnormal stage of the time series. Like uh, at certain time interval, the time series the data comes to the high, which is normally unconsiderable, but that is actually what is noise. And here the residual should exhibit constant variance. This is the characteristics of error. The mean should be constant, and the residual, what actually this is, this we called as an white something, white error or something like that, what we used to say, or we usually say is that the character error should be like constant, zero, mean indicating no systematic bias. The residual should exhibit constant variance, meaning the spread of residual remains constant over time. Yeah, that's what's actually characteristics of noise. And it represents leftover after other component are accounted for. Noise can distort forecast and must be minimized or smoothed by for better accuracy. Here by using things like exponential smoothing or filtering. Yeah, we know the noise can actually uh, brings inaccuracy in our model and distort forecast, and we should minimize that. We actually know that. Let's not talk more about it. And let's get into the time series decompositions finally. Time series decomposition is a statistical method that breaks down a time series into its individuals. You have a time series like here is, let's again get into the plot. Mm, you have this plot, and you want to decompose the time series, like what how this time series is built, and we're gonna see all about that in the time series, like these data points, these individual data points, how it is constructed, how it comes here. This is all compositions of the all three components of trends, seasonality, readers, and yeah, this and that we're gonna decompose in the time series decompositions only. Underlying the components, yeah, breakdown of time series into its individual. There's actually this is all time series and breaking downs, like you have a chart here. In this, yeah, you can see these three all are same time series, and we have decomposed one seasonality, one trends, and another we have an where it got noise, this all are the decomposed version. Yeah. In this same time series, we have traced the trends, upward trends, and how the seasonality in the same time series is like it is cyclic, yeah, and how the noise is behaving in the time series. Here we have a trace that also. Here you can see like this is trend, and if we plot the seasonality, this is gonna be like not more uptrends, but it is slightly late. What do we get? Slow. What do you used to say? Yeah, that and the residuals are already shown at the peak values, peak data. Yeah, that actually is the time series decomposition. Sorry. Think of it like you have a complex musical tracks. The time series decomposition is the process of isolating the individual instrument track, like the steady drum beat trends and the repeating guitar, the seasonality. The AI study has explained more clearly, and the random feedback or noise, the residuals. Yeah. Here it have also include all the components of the time series. The two primary decomposition methods are additive and multiplicative. When we normally additive is adding all the individual components and generally making an single outcome, and multiplicative model also has same like that, but adding up all the components in the addition additive models. Likewise, in multiplicative model, we are multiplying all the components of time series. And when to use additive models and when to use multiplicative, what we're talking about this is when the seasonality is constant, I think. What something like that. When did you, yeah. Use an additive model when the magnitude of seasonal fluctuation doesn't change as a trend change. Yeah. What is actually saying is uh, if the trends change, like here we have the upward trends. Uh, if the trend changes, like after the certain point, if the trend changes, okay, let's plot board, whiteboard. How to use this, man? Oh yeah. Okay, let's. Okay, consider this is our graph, let's say, and okay, talking about the when to use the uh, additive model is if our data is showing like this trend. This is upward trend, yeah. This is upward trend. And oh, sorry. I think we have an scale, no scale. Yeah, here we have. Oh shit! What I yeah. This is upward trend. We trace as an upward trend, and after this, the trend gone opposite. Like it decrease over the time. Oh shit. Yeah, it decrease in such a way, and our trend just from here what is this, man? Yeah, our trends look, yeah, our trend comes with a downward trend. And if the seasonality doesn't change, like seasonality, here we can trace about, like, this is what seasonality is. Yeah, it is so much random, but let's consider it. If seasonality doesn't change, while upward trend it comes with the same seasonality, and after downward trends also it doesn't change, it remain constant over every trends. Then in this case we will use the additive models. And when to use multiplicative model is if our data, if our seasonality change with change in trends. uh, yeah, like initially okay, I think we have sign up for free. We can do it this also, I think, like something like this. Yeah, okay, it is nice. If our trend, we have an upward trend. Yeah, we have an upward trends, and uh, our our seasonality is like this. Yeah, and after a certain time, time t, and again the, if this trend changes, it is just opposite of uh, additive model. Yeah, if our trend changes over the time, that it is decreasing trends. And in such cases the seasonality also changes, like in upward changes uh, hmm, the seasonality, let's say we have like this boundary of 50, and after occurrence of the downward trend the seasonality decreased. Yeah, and decrease, like it's, let's say 30, then the trends affect the seasonality. So in this case we use the multiplicative model. Yeah, here you can see roughly constant over time doesn't change. The seasonal variation remains constant. Like here you can see during the upward trends it all remain the same. And formula is just adding all the components, non other not so complex. In the model the component are multiplied together. Yeah, this is our outcomes, and the multiplying all the components helps us to find out the time series. When to use a multiplicative model when the magnitude of seasonal fluctuation is proportional to level of trends. As the trend increase, the seasonal variation get larger. Yeah, as I have mentioned, like trend increase. Oh, sorry. I said that on increasing the trends, the seasonality remains constant. The magnitude of seasonality is 50, and after decreasing the trends, the trend, the seasonal value variation comes in magnitude of seasonal variance comes in 30 range of 30. I think that was not a good one, but according to the definitions, the a change in there is proportional and they are proportionally related between what magnitude of seasonal fluctuations and the trends level of trends. An increase in trends also increase in the variations seasonal variance sorry variations. Yeah, that in this case we're gonna use the multiplicative model. And another we have here practical tip. Yeah, we can transform the multiplicative model into additive models by multiplying the multiplicative model with log, taking logarithm of the time series. We can do it here. Common decomposition methods, we not gonna cover this one, but what we will discuss is why do we decompose of time series is it helps us understand the how the it helps us understand how the trends is affecting, how the seasonality is affecting, how the noise is affecting in the time series. That's the better understanding. For the better understanding, we decompose the time series. It helps you understand the fundamental pattern driving your data. Is the recent sales increase due to the real upward trends or just normal seasonal variation? Improved forecasting. Here, you can forecast the trends and seasonal components separately and then combine them to create a final forecast. Yeah, you can separately forecast about the seasonality, like we have traced earlier, that seasonality in different chart and trends in different charts. And afterwards, after forecasting individual components, we're gonna merge them and create a final forecast. And seasonal adjustment, by removing the seasonal components, like uh, in overall time series, uh, like seasonal adjustment means how uh, no let's say how other component is affecting in collective way, uh, after separating single component. Here you have say you can see seasonal adjustment when in the over the time series we you have deducted the seasonal components here. And what outcomes does it come after uh, not after excluding the seasonal variation in the time series? In that sense we use this it helps the time series decomposition help us in seasonal adjustment. And another we have an analogy detection. After removing the predictable trends and seasonality, you can live with the residuals. Yeah. Residuals actually helps to detect the anomaly, and like large spike or unusual pattern in this residual can point to an anomaly or structural break in the data that needs investigation. Yeah, the abnormal states in the time series is considered as a noise, and the unique one which is apart from the other actually detected as an anomaly and treated as an, and it's gonna be and we gonna further investigate on upon it. Yeah, that's actually why we use the time series, why the use of time series decompositions is. This is all about applications. And that was for today. Here is the example of decomposition plot. Observe the original time series data, trends, the extracted long-term trend, seasonal, the extracted repeated seasonal pattern, the leftover random noise. And that's all about the components. And yeah, this was for today. Thank you.